The analysis of the first price auction is considerably more complex than analyzing the second price auction. In fact, the Bayes-Nash equilibrium depends on the distribution of the valuations, unlike the second price auction. We're going to make some simplifying assumptions to keep our analysis at a reasonable level. Without these simplifying assumptions, if you wanted to just work with the general distribution over the valuations, then you would have to set up some differential equations and solve them to find the Bayes-Nash equilibrium, so we won't go there. We'll restrict attention to the case where there's only two bidders. And the valuations V1 and V2 are still, just like when we analyze the second price auction, we'll assume that they are between 0 and 900. However, we'll assume that they are drawn from the uniform distribution. When I say uniform distribution, I mean that every number between 0 and 900 is equally likely. The reason we're going to work with the uniform distribution is that it has a very nice property that if you take any y, the probability that vi is less than or equal to y is just y over 900. And so that makes life easy for us when we try to do our calculation. So we're going to therefore assume that this is the distribution according to which the valuations are distributed. So V1 and V2 are both uniformly distributed over 0 to 900. Since both V1 and V2 have the same distribution, the players are sort of similar before we know what V1 and V2 are. So we'll look for what's called a symmetric Bayes-Nash equilibrium. So the strategies are going to be the same. So what each player will do as a function of their valuation is the same. Remember that a strategy here is a function from your valuation to what you should bid. So given a valuation between 0 and 900, your strategy tells you what you should bid. Symmetry says that they both use the same function. In fact, what we're going to do is to guess that the bid functions, so B1 and B2, have a very particular form. I'm going to say guess. It's not really a guess. Because of this uniform distribution, things are nice and linear. Moreover, anyone whose valuation is 0 ought to bid 0. So given that, it's not too much of a stretch to see that the bid function ought to be linear as well, such that player I is going to bid when their valuation is Vi, some number alpha times Vi. So it's going to be this linear bidding function. So what we're going to do is we'll assume that J plays according to this, and then we'll show that I's best response would be to play Bi of Vi equals alpha Vi. In other words, that would have to be an equilibrium. So let's start with some given valuation Vi. If I bids X instead, and he wins, what's his payoff? Because this is a first price auction, it's just Vi, the valuation, minus what bidder I pays, which is his bid, which is X. Now we should ask ourselves, what's the probability with which I wins when he bids X? But that's just the probability that bidder J's bid is less than X. So it's the probability that Bj of Vj, which is alpha Vj, is less than X, which is in turn equal to the probability, just simplifying this, that Vj is less than X over alpha, which, because we're working with the uniform distribution, is X over 900 times alpha. Now let's look at the payoff that I get when I wins bidding X. It's this thing. So I's expected payoff from bidding X, the probability that I wins times payoff if I wins, which is, as we've seen, X divided by 900 alpha times this thing, Vi minus X. Of course, I would like to decrease X so that this payoff increases, but there's a trade-off because decreasing X decreases the probability with which I wins. So I would have to trade these off against one another. So I's going to solve the following maximization problem. Choose X to maximize your expected payoff, which is X divided by 900 alpha times Vi minus X. The first order condition is Vi divided by 900 alpha minus 2 divided by 900 alpha times X has to equal 0, which means that X equals Vi over 2. The 900 alpha on both sides cancel, so we just get Vi over 2. So when player I's valuation is Vi, I should bid Vi over 2. So the bidding function player I is 1/2 times Vi. So what we know now is that alpha has to be a half. If we did this from player J's perspective, setting alpha equal to a half, we would come to the same answer that bidder J should bid half of J's valuation. So these two bidding functions, B1 of V1 equals V1 over 2 and B2 of V2 equals V2 over 2 is a Bayes-Nash equilibrium. So we see here that in the first price auction, you don't bid what your valuation is. Because if you bid what your valuation, Whenever you win, you're just going to get a zero payoff. So you want to bid less than your valuation in a first price auction. And in this particular case, you're going to bid half of your valuation. In the next video, I'll talk about how we can compare the revenue that the auctioneer gets from the first price versus the second price auction. Now we've done this analysis here for the special uniform distribution. Like I've said a little bit earlier in this video, we could do this analysis for an arbitrary distribution and any number of bidders, not just two, but that analysis becomes a lot more complicated and you end up having to set up a system of differential equations and solve them to get the equilibrium bidding function. You can look that up. There's plenty of resources available online. If you just Google equilibrium of first price auction, you'll probably find something that points you to that. Those of you interested might want to look into that in more detail.